Hey everyone, today we're going to be starting Unit 6, which is rational functions. We're on the first lesson, and today we're just going to have a little introduction on rational functions. We begin by mentioning that ratios of integers are called rational numbers. So we have examples like 3/4 or 5/6. So when we just have numbers involved, that they're called a rational number, and ratios of polynomial functions are called rational functions. And I usually just say a rational function is when I have something over something. Some examples, something like that, x² - 4 over x² + x + 1, or like this, or like this. Again, when you have one function over another function, the top function can just be a number, that's okay. But we just, we want to be able to, in this course, identify different types of functions and what's involved with them. So we're going to begin by just sketching the graph of each function. And real simply, we're just going to plug it in our calculator. So I'm going to clear out what I have here and just draw a basic picture. We're not plotting points. We're just kind of taking the picture off the screen and putting it onto the XY axis there, because I want you to get a feel of what's going on. So if you notice, our graph is pretty much broken up into two sections. Oops, of course I took the graph the wrong way. Our graph is broken up into two pieces here. And we're going to talk about the reason for that over the course of this lesson. And now we sketch the graph of 1 over x², and we're going to see how that's going to change the picture. And in our last quick function we're going to graph, we're going to have x over x + 1. We're going to sketch this graph, and notice it's a little bit different now. Okay, it's a little bit harder to picture. Basically, we kind of have like two things going on. And we're going to learn about these things over the course of the next couple of days. And our graph looks like it's up here and kind of down here. Again, notice that those grids or those asymptotes don't show up in our calculator. So we're going to learn how to find them. We're going to get rid of our calculator. Okay. So we already know with rational functions, we have domain issues. In addition to that, today we're going to be talking about basically our vertical asymptotes, our points of discontinuity, and we're going to save horizontal asymptotes for tomorrow. So before we begin, let's just kind of point out like our vertical asymptotes in each of these graphs. Okay, so you just, kind of take a look at where those vertical asymptotes occur. And if you notice, they kind of occur where the denominator equals 0. Okay, so our vertical asymptotes, or our points of discontinuity, are going to be affected by the domain of the function. So let's go back and talk about what the domain of the function is. It's limited to the values for which the function is defined. So we know from our previous work in this course, to identify the domain of the function, we're going to set the denominator equal to 0. And we exclude those values from the domain. Okay. So we can call these excluded values or restricted values. And remember, these are going to be values that we exclude from the domain. Okay. So for the first three examples, this is going to be like what we did a couple of weeks ago in our functions unit. We're just going to find the domain of each of these. So find the domain, we set the denominator equal to 0. So if -5 makes our function undefined, our domain is x can't equal -5. Remember, it's all the real numbers except for that value. x² - 4 equal to 0. So our domain x can't equal plus or minus 2. And again, we're assuming we have all real numbers except those values. So x can't equal 1. So now these restricted values are the values excluded from the domain of a rational function. And they're going to give rise to what we call vertical asymptotes or holes. A vertical asymptote, when it occurs, describes the behavior of the graph when x is close to some number c, and that c is going to be our restricted value. This type of asymptote does not show up on your calculator, and the graph of the function will never intersect this, so you will never cross over a vertical asymptote. So an example of a vertical asymptote would be, if this is x equals c, okay, an example could be something like this. And so we would say, as x gets close to c, our y values are going to infinity. Sometimes our graphs will go in opposite directions. So from one side, I'm going to have positive infinity, and from the other side, I'm going to negative infinity. Okay, we're going to call this asymptotic behavior, and we're going to speak about this more later on in the week. Today, we're just going to be learning how to find where these vertical asymptotes exist. A hole is a point of discontinuity in the graph of f of x. It occurs when the x value has no answer. So on our graph, it's going to look like a missing, to us, it's going to look like a missing point. So if we were sketching a rational function, for instance, something like this, we're just going to have a place. So when I plug in C, I don't get an answer, but as I plug in numbers close to C, I do get answers. Okay, so we're going to work on how to find these. You will not see this show up on your calculator. Okay, you won't see a hole on your calculator, so we have to know how to find them. So to find any vertical asymptotes or hole, we're going to factor our function, and we're going to simplify if possible. And basically what's going to happen is you identify the vertical asymptote, that it's the factor that does not cancel or cross out. And the hole comes from the factor that does cancel. So again, this is the one that doesn't cross out when you're simplifying, and this comes from the one that does cross out. So we're just going to go through, and we're going to identify any vertical asymptotes and or holes from each function. And we might want to start just by getting an idea of what the domain is. So quickly looking at this function, I know that my domain is x can't equal plus or minus 2. So I'm going to go back up top, and I'm going to try to simplify this. So I'm going to factor it. And I try to simplify. Since this doesn't simplify, it means that nothing's going to cancel out. So both of these restricted values are asymptotes in the graph of my function. In the second example, x plus 3 over x minus 1. It's already in simplest form. My domain is x can't equal 1 since nothing cancels out. I have a vertical asymptote at x equals 1. And remember, this is our restricted values, values we can't plug in, and this is what they are in the graph. The value I can't plug in, and this is what it is to me in the graph of the function. Let's look at this next example and see what happens. So my restricted values, 2x squared plus 12x equal to 0. So x can't equal 0 and x can't equal -6. That would be my domain. So now I want to figure out what's going on at these places. Is it a vertical asymptote or will it be a missing point? So I go back up to my original function, factor it, and then when I go to simplify this, I notice that my x plus 6 factors. And I'm going to go ahead and I'm going to write this in what we're going to call simplest form. Okay, so we're going to be using this form as well. So this is my factored form, and this is my simplest form. So now when I'm looking at this in factored form, before I simplify it, I'm looking for the ones that when x equals 0, that factor didn't cancel. So I'm going to have a vertical asymptote when x equals 0. And the excluded value of -6, well, that factor did cancel. So I'm going to have what I call a hole when x equals -6. Now, if I want to find the actual missing point on my graph, I'm going to plug it in into my simplest form to get the y value. Because now that I removed that issue, that x plus 6 factor in the denominator, now I should get an answer. So if I plug in -6 minus 6 over 2 times -6, now I would see I get -12 over -12, which gives me a y value of 1. So basically, on the graph of this function, I'm going to have a missing point at the point -6, 1. And again, in a couple of days, we're going to put this all together and graph it. Today, I just want you to be able to find what these values are. Now, let's look at number 4. G of x equals x squared minus 9, x squared plus 4x minus 21, and I'm looking to identify any vertical asymptotes or holes in this graph. They all come from my restricted values. So I know my issues are going to be when x equals -7 and x equals 3. If I was identifying the domain of this function, I would say this, even though it's not in the instructions, I'm just kind of including it as we work through. Now I go back up top and I'm going to write my function in factored form. And I see from factored form, when I go to cancel any common factors, I'm going to have a vertical asymptote when x equals -7. And I'm going to have a hole in this function when x equals 3. So your restricted values are always going to be one or the other. If you wanted to find the missing point, you would use the simplest form, right? And you would go ahead and plug that x value in. 3 plus 3 over 3 plus 7, and you would have a missing point at 3, and this is 6 over 10. 2 goes into 6 3 times, or 3/5. And in our last example, really quickly, my domain, I could see right away x can't equal 1, so we just want to figure out what this is. Factor this guy. My simplest form is x plus 1, but I don't really care about that right now. All I care about is that factored form. In the factored form, the factor that cancels is going to be the x value where a hole is going to occur in that graph. And if we wanted to find the missing point, we would plug that in. So 1 + 1 is 2. So our missing point would occur at the point 1, 2. And even though we wouldn't see it in our calculator, if we were graphing by hand, we put a little open circle there. Okay. So again, that was just a little bit of algebra involved in finding missing points missing points and vertical asymptotes in the graph of a rational function. Now I'm going to look at a picture of a rational function. We're going to look at a picture of a rational function. I don't have an equation in front of me, okay? But could you identify what's guaranteed to be in the denominator? So what factor or factors are guaranteed to be in the denominator of this equation? Well, if we look, I've got a vertical asymptote here, and I've got a hole here. So that means that at those two places, when I plug in -3 and when I plug in -2, those are my values that I'm restricting from my domain because I don't get answers. So x + 3 has to be in the denominator, and x + 2 also has to be in the denominator of this function. I'm not sure what's in the numerator, but I know that those two have to be in the denominator. In part B, what factors are guaranteed to be in the numerator of the function, but not in the denominator? We didn't really talk about this, and I'm actually going to hold off. Okay, so we're just going to ignore this right now. Okay, if I was to go back up here and change this, tweak this question just a little bit. What factor is guaranteed to be in the numerator? Let's think about that. What factor has to be in the numerator? Well, obviously, if we think about our factored form, the vertical asymptote is going to come from the factor that doesn't cancel, and the hole is going to come from the factor that does cancel. So that has to be a guaranteed factor in the numerator. There could be other ones, and there are other ones, but right now that's about all we can do. So tonight, your practice for your homework is really just going to be identifying, getting the function in factored form and identifying that from that form, whether or not that restricted value is going to give you a hole or an asymptote. Okay, thank you and see you soon.